Welcome to the fourth video on advanced algorithms. In this video we'll talk about greedy algorithms and we will demonstrate the ideas on the same coin changing example that we had in the previous two videos. We will use this video as an opportunity to talk about how we reason about the correctness of these algorithms, greedy algorithms, and also dynamic programming algorithms. The example is quite simple, so that will enable us to demonstrate the principles using the simple example. So let's say we have the same problem of changing 12 krona, but we have a slightly different set of coins available. We have denominations of 10 krona, 5 krona, and 1 krona. You could solve that with one of the two dynamic programming algorithms that we designed in the previous two videos, but it turns out that in this case it is quite obvious that a simpler algorithm and more efficient algorithm would work in this case. So when you design in general, when you design a greedy algorithm, you still have to think about the same things as when you design a dynamic programming algorithm. You have to think about what kind of sub-problems can you identify and what choices do you have when solving a given sub-problem, and then when you make a choice, what other sub-problem or sub-problems arise. Then, in contrast to a dynamic programming where you say you look at all the possible choices, consider what would happen if we make each of these choices, solve the value of the optimized variable for each of the choices, and pick the best choice. So that's the brute force aspect of a dynamic programming algorithm. When you are designing a greedy algorithm, you want to identify what choice is the best without considering all of the choices. So if you can design a strategy to choose a choice that you can prove gives the optimal property without actually checking all the choices, then you have yourself a greedy algorithm. Obviously, you cannot always do that. And obviously, when you can do that, then it's more efficient than considering all the choices with a brute force. So either you prove it that your greedy choice gives you the correct answer, or you shoot down an idea of a greedy choice by giving a counterexample. So we will see. We'll see how we do that. So in this case, what is a greedy choice and what is a subproblem? So first of all, we consider the same subproblems as we did in the first version of our dynamic programming algorithm. We said our subproblem is just to say how many coins we need to change the amount A. So that's the subproblem. And then the choices that we have, given some amount A, we can choose any of the available coins here. Obviously, only those coins that are small or equal than the amount of money we want to change. So the obvious greedy choice is to pick the largest coin with a intuition that the largest coin will reduce the amount that we want to change by the largest value using only one coin. So that's the greedy choice. The maximum denomination small or equal than A. And then the remaining subproblem is to change the amount reduced by the value of the coin that we have picked. So now we either have to prove that this greedy choice actually always leads to an optimal solution, or we have to shoot down that idea by giving a counterexample where it does not work. So what we want to prove is that taking the largest coin smaller than the amount always leads to an optimal solution. And these kind of proofs are usually done by contradiction, where you say, let us assume that we have an optimal solution for the given amount A, but that solution does not include the greedy choice, whatever that is defined for the given problem. And then we show that by modifying the solution so that it includes the greedy choice, you do not make it worse. You make it better or the same. So that's the idea. So let's say SA is optimal, but it does not include the 10 krona coin, and we know that the amount that we want to change is larger than 10. So we could make a choice of taking 10 krona. We just have to carefully look at all the cases and show that we can improve the solution SA by using the coin 10 krona coin. So let's say if SA contains only 1 kronas, then obviously we could take 10 1 kronas and replace by 1 10 krona, and this would obviously improve SA by reducing the number of coins by 9. Let's say SA contains just 1 5 krona coin and then some 1 krona coins. Then we can improve this SA by replacing this 5 krona plus 5 of 1 krona coins with 1 10 krona coin. So instead of 6 coins, we have 1 coin. So we improve SA by 5 coins. And finally, if SA contains more than 1 5 krona coin, we still can improve it by replacing 2 such 5 krona coins with 1 10 krona coin, improving the solution by one coin. So that's in every case. Here we see that this leads to contradiction. We said that it's assumed to be optimal, but we show that we can improve it by using 10 krona. We have to look at all the cases. The remaining cases when the amount is between 5 and 10, then we cannot use 10 krona, but we, as the greedy choice, we take a 5 krona coin, and then let's assume that the optimal solution does not have this 5 krona coin. What that means is that the solution is just composed of 1 krona coins, and we obviously can improve it by replacing 5 1 krona coins with 1 5 krona coin. So in this way, looking at all the cases, we show that in each case this leads to contradiction. So we have shown that making the greedy choice always leads to an optimal solution. In this case, it was quite simple for these kind of coins, and it is quite obvious that the greedy choice makes sense in this case. For some other coin denominations in this in this kind of problem, the proof may be a little bit harder, and we may consider more cases. So, for example, all the monetary systems of most countries have this so-called 10-5-2-1 system, and it can also be proven that in these systems the greedy choice works in this case. If for some problem you cannot prove, you're not successful in proving a candidate greedy choice property, then it may be that the idea is wrong. And what you have to do is you have to convince yourself that that is a wrong idea for the greedy choice. And to do that, you just need to show one counterexample where it does not work. So for example, if we have the denominations as they were in the previous two videos, so we have a 6 krona denomination instead of a 5 krona denomination, then we can shoot down the idea of taking as a greedy choice the largest coin that is smaller than the amount by just giving one counterexample. Like in this case, the greedy algorithm would result in the solution of taking 10 krona and then leaving with us a problem of 2 krona, which is obviously solved by taking two 1 krona coins. And this is obviously not optimal. The optimal one is 6 plus 6. So just giving one counterexample, we immediately show that this greedy choice does not work in this problem setting. Finally, the last thing we have to look at if we want to convince ourselves that our greedy algorithm is correct, and also if we want to convince ourselves that our dynamic programming is correct, is to show a so-called optimal substructure for the problem. So I talked about that in the lecture, but specifically for this problem, that's how we would have to formulate it. We have to show that if DI, some choice, in this case choice of a coin, is in an optimal solution S, so there is some optimal solution S where this is actually part of it. So in a greedy algorithm, we prove, we know which choice to make. In a dynamic programming algorithm, we look through all the possible choices. But so if we assume that DI is in an optimal solution S, and it generates a subproblem, in this case, this kind of subproblem, or it may generate in some other kind of problem, it may generate more than one subproblem, it may generate 2 or more subproblems. Then we want to show that if you take this optimal solution and remove just this choice, so take the remainder of the solution, we want to show that that remainder is an optimal solution to this subproblem. So in a sense, you are justified by looking for an optimal solution of this, because if you find an optimal solution to this, then you can replace this thing in an optimal solution with an optimal solution to this, and you will have the same cost of the solution. If you had this kind of solution, then, and you know that 10 is part of it, then you just have to show that if you look at the rest of the optimal solution, that part is an optimal solution to a subproblem of changing 2 krona. Obviously it is in this case. And for this situation, this is very obvious. You can show this by this cut and paste argument. In this case, if you had better solution, if this were not an optimal solution to this, then we would improve the whole S by replacing this part with a better solution to this one. So that works in this case, the cut and paste argument, but in general it may not work. As I have shown in the lecture for the examples of the longest simple path in a graph or a clique,